propane do I need to heat up the air from its beginning to its end? But you have to take into account the change in the moisture content of the air, that's all. And that includes the fact that the propane produces some water.
All right, units. All right. So besides combustion calculations, what else about this spreadsheet shall we move on? Bonnie.
Okay, so if we scroll to the very, very start of your spreadsheet, Dr. Masanti.
Which spreadsheet? This one?
Yeah, SimCalc. Great, thank you. The entry that I'm interested in is called dry air entering the spray dryer. You might have named it something different. It's going to be difficult.
So, do you have a line?
Line of it is 219.5.
Sorry, can you give me the column and the...
I've actually rearranged your entire spreadsheet, so that's going to be not...
No, no problem, but so where would it be? Or
it's...
Is a dry bulb temperature?
No, it's called dry air entering the spray dryer. It's calculated, it doesn't matter how it's calculated. The number is 219.5. Hopefully it's visible somewhere close by.
Oh, there it is. Exhaust, just keep going down. Is it, yep, room air flow reviews, 219.5?
Here?
Yeah, okay, great. Yes, so the room air flow reviews, can you just explain a little bit what you meant by the name that you've given to that stream?
So, this is, actually probably we're going to call this moist air flow rate. So, we calculated, or I calculated here, the amount of dry air that we have, let's say here, right? That's the dry air, right? And here is the air that came into the chamber from the outside. So it would be how much air I'm actually sucking. And it includes the dry air and the moisture that came from the room to the combustion chamber, including the moisture that it sucked from the room.
Great, thank you.
Dr. Masanti?
Yeah,
You go to calcs moist air, please.
the example, this one.
Yeah. Number 2, I'm not sure what we're given versus what we're trying to calculate because everything seems to lead to another cell, which leads to another spreadsheet. So, what are we doing?
All right. So, if you want to, for example, what if you want to, if you have a dry bulb temperature and a moisture content, this moisture content should probably be 35, 3.5. And then you want to determine things like the wet bulb temperature or I'm sorry, here we were given that, right? Let me remember how this was.
You're given what's in the box only?
Because this I did longer earlier. So we have these two pieces of information, right? And we want to find things like wet bulb temperature. So what this is going to do is going to do some little kind of iterative calculation to try to find that wet bulb temperature, okay? So we're going to get first, okay, let's start initially. You see this is feeding itself back from that one. So the way to start this is to, I'm going to write this number here as a number. And then I'm going to put here 36 or something like that. So now it's just some guess, okay? And then we're going to follow where it goes. So there are two cells that depend on that one. Okay? And those are these two enthalpies here that depend on that one. And those enthalpies are the enthalpy of air at saturation temperature and the enthalpy of the water vapor at the saturation temperature. Okay? And the reason is that we're going to try, this is how to find using a kind of an iteration rather than solving the equation. And in the case where you use constant specific heats. So what we did here is we found this is the enthalpy at the enthalpy of the dry air and the enthalpy of water vapor at the saturation temperature, if we knew it, and assuming constant specific heat.
For the HWA, the unit is given kilograms of dry air. Is that?
Not wait for the green ones yet. No, we haven't gotten to the green ones yet. Now on the other hand, these two here come from the temperature that we have there. So if I trace the dependence here, they are these two cells here. So these two cells are the enthalpies calculated, the exact same enthalpies, but calculated using the dry bulb temp. Okay, so those are the enthalpies that correspond to the dry bulb temp. So when do we have the same enthalpy? Only when the dry bulb corresponds to the wet bulb. So you guys, you can see this. So one way I mentioned yesterday to get the wet bulb temperature. Suppose we have a moisture content. We have now a moisture content, right? We have been given a moisture content, and we have been given a dry bulb temperature, and we are asked what is the wet bulb temperature. Sorry, this temperature is not there. So we want to know where is that wet bulb temperature. So what we need to find out is what is that wet bulb temperature. So one way of doing it is to assume that the wet bulb temperature is going to be the temperature at which, at that same enthalpy, okay, same enthalpy, we're going to reach a point where this wet bulb temperature is going to be the same as the temperature. They're going to have the same enthalpy. So with my definition of enthalpy, there's going to be another moisture content here at saturation that's going to, at another temperature of saturation, it's going to give me a temperature. And this temperature of saturation is the same as the wet bulb temperature. So if I calculate this enthalpy first, with the data that I have a moisture content and temperature. That's all I need to calculate enthalpy. Those two pieces of information, the only two pieces of information I need to calculate enthalpy. Once I have enthalpy, I can calculate the temperature of saturation, because the moisture content at saturation depends on the temperature. So at saturation, I only have one variable for the enthalpy. So what we do is we calculate this, although it's there recursively, it could be done algebraically. So we calculate here first from the temperature here at dry bulb, we calculate an enthalpy here. And then with that enthalpy, we use that enthalpy, the same enthalpy, and we use those partial enthalpies to recalculate an estimate of that wet bulb temperature by using the vapor pressure of the water, by using the partial pressure of the water and the temperature of saturation with Antoine, like we did yesterday. And then what we do is we correct that wet bulb to the new calculation, and then through iterative calculations, it does it to itself. But it could be done algebraically. Could be done algebraically. With the constant CPs, no? With the non-constant CPs, then no, because it would be cubic. So all we are doing is applying what we learned yesterday to solve when you are given. So given, find. Okay?
So you couldn't use the functions for CP in those
Yes.
cells?
Yes. Yeah, but this was developed long time ago, much before I did that.
So if we were to not use just the fixed CP values in there, it would work just fine? Like if we
No, the values are not so I mean, the higher the temperature range, the more you will depart from the actual data that you would read from the psychometric table. That's all that's going to happen, and you're going to start getting, I mean, the errors in the enthalpy start becoming 1, 2, 3, 5, 8 kilojoules per kilogram, and then you start departing. It's a matter of how accurate you want your representation to be on the psychometric table. So that's why I decided to include that. So you guys, when you guys get the data on the psychometric table, you don't start getting your points more and more distorted from what you see in the psychometric table. But conceptually, it's the same. It's just that the CP is a function of T, and then we have to live with that.
So for 38 temperature dry and 49.1, these are just like examples to show us how the relative humidity percentage changes?
Yeah, yeah.
Okay.
So this is one way of doing that. If you were to replace those CPs with the equations, it would still work because it's an iterative calculation. You would get a slightly different value. And the higher you go, the more this will be different because your CPs are going to be more and more and more away from those typical values that you find in those values are used a lot for the people that do like ventilation in buildings and stuff like that. So the type of air that we use in ventilation is in a very narrow range, the temperatures that we use. So you can use those values, no problem. But in drying, especially, and if you guys are in things like cement industries or stuff like that, then you go to even higher temperatures. Then you really need to use the functions at those higher temperatures.
For part question 4.
Yeah.
Can you explain how you use ln of H and ln of MCS?
This is just a very, very empirical, completely empirical thing that I did, just to because in this process here of when you have the enthalpy, right? When you have your enthalpy and you want to find your wet bulb temperature, for example, right? It's an implicit equation, and if we get some enthalpy somewhere, and I mean, for us as humans, it's very easy. We just glance at the psychometric chart, and we can get a good guess of an initial value of the wet bulb temperature, and then do our Newton estimation, and we get a good value. But I wanted the program to be able, or Excel to be able to do it automatically. So I needed kind of a value that was relatively close. So I was curious to see, well, could we have a rough, very rough empirical relation to at least initiate that process? So I plotted these two functions. Well, I did several other plots, but these ones seem to kind of have some degree of correlation. I was not looking for a perfect correlation. It was something that landed me close enough to start an iterative search, right? Without having to suffer too much. So I did the three sort of correlations that these things could have, and the one that I ended up using was when I have the enthalpy and I want to find the wet bulb temperature, because that's the case that's more difficult. The temperature is everywhere in the equations, in the cubic, and it's in the exponential of the vapor pressure, and it's pain in the ass to find. So what I did is if you plot the natural logarithm of the enthalpy and the temperature, then you can find a correlation. And what you have here is the three Linest functions of that. That's all it's there. And you have a plot there that you can move around. I just selected two of those, but you can select two, but you can take this one, you can take that one. So this is enthalpy, moisture content at saturation, and wet bulb temperature. So anytime we want to try to find something here, we can use any of those functions to our convenience. And this is done a lot in engineering, only in chemical engineering, but in general, which is to have some kind of empirical functions that allow us to come close to some solution, and they are not necessarily perfect. Right?
Could we pull up the front panel again?
Yeah.
So from the front panel, has anyone yet put in their lab data? Nobody? Does everyone understand how you would put in your lab data?
For example, we put the most of you guys operated with the dial at either 0.8. Most of the milk experiments were done with the dial at 0.8, right? And now the pump is calibrated a little bit different, so maybe the flow rate that you get there is not exactly the one that you think you had, but probably close.
And everyone knows how to calculate the solids in the milk stream?
Usually, what percentage of solids did everybody have?
Yeah.
Let's say 20? So let's put 20% there. And most people operated at 210, although some groups I know operated different, but let's say 10. And does anybody remember a typical dry bulb, wet bulb combination of the air of the room?
23 and 12, that's a good one.
And temperature of the feed. Did anybody measure the temperature at which you were feeding the milk?
We estimated it would be at what temperature? 25 degrees.
Oh, 25, no, now it's much more. It's not 25.
Ours was 24.
24. 24, 25, okay, 25. Well, those are sort of the parameters that we can actually control. The way this is set up would require me to go in here and do some iteration here of my output temperature, although I think finally I kind of played a little bit. I think I can try it here. Let me see if it will crash or not. I did like an indirect iteration. No, now it's doing. If I don't do it directly, if I do it like this. You see what I just did? This used to be a number here, right? See, it's a number I have to input, try to match it with this one. So I have to guess a number and then, but now it turns out that if I make it equal to that one, when I made this number equal to that one and let it run through its iterations, sometimes it crashed. So now I do it, but it didn't crash, so let's see.
So if you are trying to get the temperature of your product throughout...
The temperature of the product has to always be, the product cannot go out warmer than the air that's going out. How is it going to do that?
Has to be between two
And
numbers.
if it is evaporating, it would have to be at a temperature higher than the wet bulb temperature anyway. It has to be in that range. So now what I did here is I am just having loop automatically instead of manually. What I just did.
So making certain assumptions about that final product temperature, knowing how to optimize the system, and knowing how to input in your data is going to be very important.
So basically this is what I would get. I would get that the output temperature is estimated to be around 100 degrees. I don't know if that is consistent or not with what you guys got. But that would depend, of course, on the velocity that we choose. And I have 1600 feet per minute here, which may or might not be